So we have seen the different flip-flops, advantages, disadvantages of each flip-flop, and we know the truth table or the characteristic table and the characteristic equation of each of the flip-flops. Now next is the excitation table. So excitation table, see what is the difference between a characteristic table and an excitation table? In a characteristic table, we know the, what do we know? We know the previous state, we know the inputs. If it's a SR flip-flop, we know SR. If it's a JK flip-flop, we know the value of JK. If it's D, we know what is D. If it's T, we know what is T. So previous state and the inputs we know. Knowing the previous state and the inputs, what we are finding out is the next state. So that is the characteristic table. Now in the case of excitation table, so in characteristic table we know what the previous state is and we know what we are going to give as the inputs. So what will the next state be? So if we want to predict what the next state is, knowing the previous state and the inputs, then we will use the characteristic table. And excitation table is knowing the previous state, we know what the previous state was and we know what the next state should be. Previous, present. We know what Qn was and we know what Qn plus 1 should be. So knowing the Qn, we want this Qn plus 1. For that, what should we give as the inputs? That is decided by the excitation table. So we know the old state and the new state. We want to know what should the inputs be in order to get Qn plus 1 if the Qn was this. In the characteristic table, it is knowing the previous state Qn and we are going to give this input. What will the next state be? So that is the difference between the characteristic table and the excitation table. So we'll take each flip-flop. First we'll take the SR flip-flop. We have to derive the excitation table of each of the flip-flops. So SR flip-flop, we will derive the excitation table from the characteristic table. Okay, so we'll write the characteristic table of SR flip-flop. So we'll just write it like this so that it's easy to write the excitation table. Okay, we are just writing Qn here. So for this, S0 R0 means Qn plus 1 is Qn. S0 R0 Qn plus 1 is Qn. S0 R1 is 1. 0. S0 R1 is 0. S1 R0 is 1. S1 R0 1. S1 R1, it is don't care or invalid. So from this, we'll write the excitation table. That is, we know we have Qn plus 1. We have to predict what S and R should be. So Qn Qn plus 1. So for that it can be 0 0 0 1 1 0 1 1. What should be S and R? Yes. So if we look at this particular table, Qn 0, Qn plus 1 0, that combination we have to check. So it's Qn 0, Qn plus 1 0, then we have this one. So if we take these two combinations, check the SR. Here S0, R0, S0, R1. So S is 0 in both the cases. For Qn to be 0 and Qn plus 1 to be 0, S should be 0. R is 0 here and R is 1 here. So R is okay. Whatever it is, it doesn't matter. S should be 0. So R is don't care. We are not bothered about R. Next is Qn 0, Qn plus 1, 1. 0, 1. Here we have a case, only one case. So for that, S should be 1 and R should be 0. 1, 0, we have a case here, S0, R1. 1, 1, we have two cases here. For that, S0, R0, S1, R0. So S can be anything, R should be 0. R should be 0, S can be anything, so S is don't care. So this is the excitation table of SR flip-flop. Okay. Now, next we will write that of JK flip-flop. So JK, Qn, Qn plus 1, JK. Okay. 0 0 0 1 1 0 1 1. Yes. So Qn plus 1 0 0. Sorry. Before that we have to write the truth table of or characteristic table of JK flip-flop. So JK 0 0 means previous state. 0 0 means previous state. 0 1 is 0. 0 1 is 0. 1 0 is 1. And 1 1 is Qn bar. Yes. So 0 0. So we will take 0 0 case. So that is this one and this one. So in this case J is 0, K is don't care. So J is 0, K is don't care. 0 1. 0 1 cases. Here we have a case 0 1 and here we have another case. So J is 1 and K is don't care. J is 1 and K is don't care. 1 0 1 0, here we have a case and here we have a case. So here J is don't care and K is 1. Don't care 1 1 1. So 1 1. Here we have 1 1 and here we have 1 1. So in 1 1, J is don't care and K is 0. Yes. So this is the excitation table of JK flip-flop. 0 0 0 don't care. 0, 1, 1 don't care, 1, 0 don't care, 1, 1, 1 don't care, 0. Okay. So next is T and D. Okay. So in the case of T, 0, 0, 0, 1, 1, 0, 1, 1. So in the case of T, T0 means Qn, T1 means Qn bar. So we'll take what? Qn plus 1. So if we take Qn and Qn plus 1, 0, 0, 0, 0 is this single case. So T should be 0. 0, 1. 0, 1 is this case. This case. So T should be 1. 1, 0. T should be 1. 1, 1. T should be 0. So if we see this itself, we know that if both the previous state and present state are the same, then T should be 0. Yes. And if both Qn and Qn plus 1 are different, then T should be 1. So 0, 0 means 0. 1, 1 means 0. If they are different, T is 1. So that's easy to remember. And next one is D. D flip-flop. D, what is D flip-flop? In D flip-flop, whatever is D, that is Qn plus 1. So Qn plus 1 is like this. So here when you take 0, 0, this one, D is 0. 1, 0, 0, 1, D is 1. 1, 0, D is 0. 1, 1, D is 1. So in D flip-flop, whatever is D, that is Qn plus 1. So reverse is also true. That is whatever is Qn plus 1, that is D. So this is also easy to remember. So that is excitation table from characteristic table.